Hello everyone, it's August 22nd. Alright, we got another easy one today. So that means we can get this one done. I'll read the other solution. Maybe we can start taking a look at design and text editor. But let's solve this one first. Palindrome linked list. Given a head, return if it's a palindrome. O1 space. Yeah, it's basically what this type of problem will ask you. Want to get O1 space. Okay, O1 space. O1 space is easy. We just go through the entire thing and then see if it's a palindrome. But O1 space, how do we handle O1 space? Basically, we want to say, we can reverse it and then compare. Ooh, compare to whom? Exactly, compared to whom? You have to set up a separate one if you want to compare. If you do it in place, how are you going to compare? O1 space. We can go half. We go half. We reverse the second half, and then we compare. But then we are making changes to the thing. So we need to avoid changes. Can we avoid change? So like we have the reverse and the reverse back. Do we want to do that? Otherwise, what other options do we have? Technically, we can just reverse and not turn it back, but I think in the spirit of this problem, we probably should do that. Alright, so we need half. Alright, we can go 1, go 2, and the other go 1. We can always use this trick to get to the halfway point. Alright, so if we have odd even number, say 1, 2, and 1. So we go 1, 2, and then we'll go 1. So we end up here. So 2 steps. Well, actually, no. If we say have to go 2, but we have even numbers, then we always go 1, 2, 1, 2, right? And then 1. So actually, we only go 1. So we end up here. Interesting. Which actually not a bad thing. How about odd number? 1. So 1, 2, we'll end up here. So we'll always end up at a point where we can reverse the remaining. Okay, so we can point this to none, and then record this thing. We call it the second start. All right, and then we reverse this, and then we have a new start. Right, then we will do the comparison. And it's guaranteed that the second half will be shorter or the equal length. So after we've done that, it's good. Then we will reverse it back and then point this one again and then return the results. Okay, so this is going to be my solution. So we need to do a reverse head, right? No, a list node, actually optional. Okay, so I need to reverse it. How do we reverse it? So we have a dummy equals list node, so next equals head, right? Then pre-current equals dummy and head, and then we're gonna say while current, right? While current, we say temp equals current.next, right? And then current.next equals pre, and pre equals current, and current equals temp. Right, so we save this, current.next point to pre coming here, and then current becomes this. I'll return pre. Ooh, return pre. Actually, we have to also say dummy.next. This is this thing. .next. It could be none. Because dummy.next is head, and then head.next equals dummy, right? Oh, I always do this. Let's return none. Right, and then we just say dummy.next is just original head.next equals none. Then we return pre. So this is the reverse. Right, and then we have slow and fast equals head and head. Right, while fast and fast.next, slow equals slow.next, fast equals fast.next.next. So once we're done, slow are pointed to the last node of the first half. Then what we're gonna do is the head of the second head. Okay. Second head will equal to slow.next. And then we can say slow.next will equal to none. Right, we shut it off. Then we say rev head equals self.reverse second head, right? So we reverse the whole thing, and then we say result equals true, and reverse head. I don't need second head because I'll get the head back. So I just need to do this. Oh, hold on, I do need it. Do I? Actually, I don't need this. Alright, we get a reverse head, so it would be this pointing, pointing to here, and this, the last one, will point into none. This thing will point into none, and then we have something pointing to this as well, but which is fine. Then we have reverse head, and we say node n1, n2 will equal to n1, let's say, is head, n2 is reverse head. Right, while into if n1.value, if n1 and n1, yeah, it should be n1.val is not equal to n2.val. These two are not the same. Then rest equals false, and then we break. Otherwise, n1 equals n1.next, n2 equals n2.next. Okay. So once we're all done, we have to self.reverse head, right? Because reverse head is here, so this one pointing blah 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 blah. Then we get the original one, and the slow already is still pointing to it, so which is fine. So we just reverse it and then return result. Okay. Let's see. This one works. It does not work. All right, the second one. Okay, while fast and slow both point to here, while fast and fast done next. While fast and fast done next. No, while fast done next. And fast done next done next. Fast done next must exist. Oh, hold on, no. What you doing, man? It is while fast and fast, so we can go one step. So fast done next done next. Oh yeah, I have to go to next. Fast on next, and a fast on next on next. Yeah, because I need to jump 2 times. And then, boom. Yeah, we can check. 1, 2, 3, 2, 1, right? And then say 1, 1, 2, 2, 3, 3. See if it works. It works, so we can submit this. Okay. It worked. I mean, if you really do this, I think it's more than an easy problem, right? So this is O n time and O1 space. Find the second half, reverse it, compare, reverse back, return. And of course, we can write a faster one. We can say this is O(n) time and O(n) space. All right, I just say array, and then node equals head. So while node dot append node dot value node dot next return this equal to this. Definitely be faster. Oh, it's not that fast. Alright, so what was the solution in the past? April Fool's Day. This is today's, wait, this is not today's solution. Oh, look at that. This is it's a without restoration. So it is the same idea. What is this? I don't know. Probably this is with restoration. No, this is today's solution. What's this? 84 test cases. Oh, wow, okay. This. Oh, this is with restoration. So I think there is change in the size. 84 was today. 87. That's why. Okay. I shall do it. So we're done with this. And I'll go back to this one. So, distance. We know the ON squared solution, which is to find the longest distance you can travel by visiting how many, like one station, 0 station, 1 station, 2 stations, right? And we can use dp because if you want to find the longest after visiting 3 stations, then we need to know the longest after visiting 2 stations. And there could be different combinations when you're visiting 2 stations. There could be the second station is the 2 stations, or the second station makes the 2 stations, or the third makes 2 stations, or 4 make the 2 stations. It doesn't really matter. But you can have a string, an array of stations that make up the second station. So you have to go through them one by one, right? Because each one will give you the maximum range that you can get after 2 stations. And then you look at your current. Your current have to start with station 3. And then you say, okay, if the previous I choose station 2, and I have the maximum range. And now I can do station 3, that makes it 3, or station 4, or station 5. You just go through all of them and find the maximum for station 2, or for station 3, right? And then you go on, okay, let's say if 2 stations is station 3, then 3 stations has to be 4 or 5 or 6. And just go through all of them. That's basically what this is, right? This is the position and the fuel of the previous. That's the current station, right? That's the current station we're looking at, and this is the previous station, the previous step, right? So the previous step. Now we say the previous step, this one saves the longest distance that can travel in this previous step. And if it's smaller than the current position, then we cannot consider. We can only do when it's larger. When it's larger, then we say this dpi nj plus 1 is the current, right? So we're considering so this is the previous j step. This is the j plus 1 step, right? It's j plus 1 step. So at j plus 1 step, we want to find a maximum reach. So at the j plus 1 step is going to be whatever it is, and at j step, right? At j step, and it's not j. It's actually, oh, that's actually not step. That's not, is that step? Is j step? Yeah, it is step. At the j plus 1 step. Wait, hold on. I'm a little bit confused here. So this is the stations, right? I is the station. And we are at the jth step. And for the jth step, not the jth step. So dp is the previous. Oof, no. Oh, no. Got a bit confused. Is the max reach at ith step? Okay. Yes. At a kth station, the maximum steps is k plus 1 because k is 0 based. Yes, the maximum step is k plus 1. Query the max reach at k and k minus 1. Yes. If at that step we can reach the kth station, oh, then we have to decide, right? We have to decide which K station to use. Yeah, I think that's the thing. Because the previous step, like if I want to go for the jth, right, the j plus 1 step, this is the next step, right? So currently we have to look at the jth step. So from jth step, I have the maximum reach. And this maximum reach, yes, I know, this previous step. And from this, the maximum reach, I can reach multiple stations, right? I can reach, since I can reach multiple stations, so, why do I enumerate the stations first? It's the same thing. I just say, okay, at the current station, the ith station, it can be reached, it can do, I steps or I minus 1 steps, right? I can do I steps to reach here. Like if I'm in a second 0, 1, 2, right? If I equals 2, then we can do 1 step to reach it. We can do 2 steps to reach it, or we can do 3 steps to reach it. So like 1, 2, 3 steps, right? 3 steps to reach it. So I want to know, by considering my current station, can I make it better? And I have my position. So I say, okay, I will look at the previous step, because for me, the maximum I can go is going to be actually the I plus 1, right? It's I plus 1 steps. So I go, okay, hold on, how about I say 2 steps, right? 2 steps. So if I is 2, so j first coming in, j is 2. So we go dp2. That's the maximum we can reach after 2 steps. And if I can reach the ith station by 2, then I can compute the maximum is going to be this plus fuel. We have gone through this, so we know. So we have the maximum of 3 steps. But then we can go down, say 1 step. If I can reach the second station by 1 step, right? If it's larger than the position, then I can say, okay, I'll update j plus 1. I'll update dp2, right? Because I always dp1, I can update dp2. That's why we have to also go from right to left. And then we can also go like dp0, right? Which means 0 step. If 0 step I can reach there, right? That means we can do 1 step even further. Makes sense. Okay, so this one we understand. How does the heap play in this? When driving past the gas station, let's remember the amount of fuel. Decide yet whether to fuel up or not. For example, there could be a bigger gas station ahead. When we run out of fuel before reaching the next station, we'll retroactively fill up, choosing the largest gas station first. Drive the largest distance possible before each refueling stop, and therefore having the largest choice of gas stations to retroactively stop at. So we choose, remember the amount of fuel it contained. When we run out of fuel before reaching the next station, we retroactively fuel up. So we try to go as further as possible, and if we can't, we fill up the largest gas station. This gas station we've driven by, we also keep track of tank. We reach a station but have negative fuel. We need to have refueled at some point. We're at the capacity of the largest gas. So we already passed it, so we can definitely reach it. So we get the largest. So when we get the largest, then we'll update the fuel until the fuel is non-negative. If at any point the process fails, the task is impossible. Oh, I think I know what this one's trying to do. So we start, right? And then we just keep tracking the gas station. Not gas station, the fuel. So we go past everything. So the fuel tank will go low. And then we don't add any gas. We just go low. And the first time it becomes negative, then we say, yes, we're going to add the maximum. And it works because that is the best strategy. Basically, we are creating the longest reach possible by refueling with the maximum gas, right? If you think about it, we go through the gas station, we are guaranteed that the gas station can be reached. And now we hit a negative, which means the current gas station cannot be reached. Now, in order to reach the current gas station, we want the maximum gas in the previous stations that we have already gone through. And the best strategy is to get the maximum fuel, which means this strategy allows us to have the maximum reach in the current stage. Now we add to it, right? And then when the fuel tank becomes positive, we'll do it again. We just keep going forward and re-adding new fuels. Oof, this is good. Holy crap, this is good. Alright, so we have solution 4. We're going to code it ourselves because I think I understood. So this is the heap solution. We don't refill, but try to reach as far as possible until fuel tank contains negative fuel. As far as possible, gas station. When that happens, we know the current gas station cannot be reached without refilling, but any of the previous gas stations can be reached. Thus, we greedily choose the gas station with the highest amount of fuel to refuel. This is where heap comes into play. Right? We will keep popping the highest amount of fuel to add to the tank until the tank becomes positive. Then we repeat the whole process until either we reach the destination or cannot progress any further. Okay, so with this we have a tank which actually has start fuel, and we have a heap which is basically just this, right? And we say, ooh, what's the first one for heap? Actually, tank shall be 0. Heap shall be start fuel, right? And we say while heap, oh, negative. Okay. While heap. Do I need to record my current position? Will this go 1, go 1, go 1, and I have the current tank, right? And then the remaining distance is going to be target, okay? And then every time we go, we can go target. We say tank, while tank. We say while tank is smaller or equal to 0 and heap so become positive. Tank plus minus equal to heap q.heap pop. Heap, okay? So we pop it out and then we'll get out. Then we say if tank is still smaller or equal to 0, then we return -1. This is not possible, yeah? Cannot progress further. Otherwise, actually we're going to do first. We say if tank is larger or equal to target, then we return, what do we return? The number or the result. Right, then we say return result. Otherwise, while it's smaller, we just adding. If it's still smaller, then we say cannot progress further. Otherwise, then we can progress further. What do? We will go as far as we can. We can say while tank is larger than 0, right? We need an index. We need to record where we are. Damn, it has to be 0. So while tank actually, we'll just say for I in range, index to LAN stations, right? Tank minus equal to the distance. How to keep the distance? Oh, and we need a current position. We need a current position. And the target minus position. So minus stations I 0 is its position minus the position, right? Tank is like that. And then we take the fuel. We'll use this fuel, we'll reach there. And we say if tank is smaller or equal to 0, down and break. Now we'll go back up, right? Oh, hold on. This doesn't look right. Hold on, that doesn't feel right to me. I feel I shall do for position and fuel in stations. And then we say, so this is the next station we want to reach. And now we take a look at the tank. And they say, oh, the tank is smaller than 0. Then we're going to refill the tank. After we refill the tank, if it is larger than this, then we return the rest. Right? Otherwise, elif, right? Elif after we refill, it's still negative, then we return this. And then we are going to say tank minus equal to this, right? And then we are going to, but how do you know we can make this move? Well, we'll make the move, right? We'll make the move, and if it becomes a negative, then we will do this, right? If it becomes negative, we will try to refill to see if we can reach the current position. And if we can refill to the current position, then we're good, right? If we cannot, so we will say this, and then heap q dot heap push. We're going to push in stations I1, the fuel, which is actually, we have fuel out, current position. So we minus current position, and this is just position minus current position. This is the next one, right? That's the amount we have to do. And then we just say current position equal to position. Then we go back up, right? If it's smaller, then we have to add something. If it's still smaller, we have to add some until we run out of heap. And if we run out of heap, coming here, if it's larger than, rest have to plus equal 1. Okay? And we're going to return, we don't have to return here. We can do this. We can break, right? And then we return -1. So make it very clear. Okay, so this is solution 4. We can try. Oopsie doozy. That looks very bad. For -1, that's terrible. Okay, let's do the first one is fail. So fuel, that's just 1 and 1. Tank is 1, yes. And then we are going to, and then we're gonna have 1. Tank gonna be 1. And if 1, the result Why would it be -1? Target, what's a target? Target is 1, right? Target is 1 minus current position. Current position is 0. What the hell? What's tank? What's target? And what's current position? Oh, we don't have stations. Damn. Alrighty, that's the problem. Okay, we can add station to it. Position and fuel, right? And so we're saying everything is gonna be like this. And stations equals to 0 and a start fuel plus stations. Nope, but I think we'll have this. Yeah, we'll have 0, target is 1, current position is 0, and target is 1, minus current position is 1. Why don't we return result? Right? What the hell happened here? Oh, tank is 0. Tank is 0. Because it's not in a heap. I say I want to reach this, right? I want to reach this. I am on it. Okay, that's the thing. I am on this. You know what? I am on it. So start fuel. Heap is empty. Okay. Then we don't do this. And this is larger than target minus current position. And then what? Oh, that's because the stations are never reached. How about we do this? Rest equals -1. Then break. And this one is break. Then we'll pass. Okay? So, by doing this, we have 1 return here. Let's try. Alright, this doesn't work. Why does it not work? Result is 1. That's rich. Hold on. So we'll start is 1. Right? Tank is 1. And the target is 100, right? And then current position is 0. Now we say tank larger than? No. Is tank smaller than 0? No. So what's the position? Position is 10, right? Tank minus, hold on, I only print out once. Result is 1. Coming up. Oh, then we go out. Damn. Okay. Okie dokie. Okie dokie. So if this, I see. All tank is smaller than 0. Either case, we're gonna break. Okay. And once we break, we're gonna say if tank is smaller or equal to 0, then we'll return -1. Right? Oh, that's actually not true. Larger equal to target minus current position. Then we'll return res. Otherwise, the only case, if it's not this, it has to be this. And if it's this, that's going to be -1. So if we do that, then we pass. This makes sense. Okay, let's try the others. What the heck? Alright, we need more. Let's see, we have, again, tank. Target is, target of 100, target is 100, and on our current position. Okay. Oh, current position equals position. Huh? Current position is 10, 20, 30. No. We are going forward. Now, okay, the result is not here. The result is here every time we fill. That's refilling. Okay. Then we go here, we go here, we go here, right? And then the tank goes down. And now we are at 40 and 30. Position is 30, right? And the tank, wait, hold on. Position is 30. And the tank is 40 left. Yes, because 10 plus 20 plus 30 that's 60. So tank has 40. Current position is here. Is it larger than? No. Because target is 100 minus current position is 70. So it's not. So tank minus position. What's the position? Okay, position is here. So position minus current position is 30. Right? Then tank minus 30. Wait, hold on. All right, sorry, so we can get here with 10. So 10 can become 10, right? 10 is 10, so we reach here, tank has 10 left. And then I put a fuel, which is 40 in it. So current position is going to be here, 60. So go tank no. Is it larger than? No, it's not larger than. It's not larger than this. And I see. Didn't go through this. So maybe we should put the last station in here. That's actually a good idea. If we put the last station in there, and then if we go through the entire thing, that means we reached. If we break early, that means we fail. Okay, let's try this. Stations.append. Target, and we have 0 fuel. And then we'll go blah blah blah, and then we won't do this. We just say if anytime it's smaller, then we will return -1, because we cannot progress further. But what if we reach the position? Yeah, we reached this, and after refilling, the tank has to be larger or equal to 0. If it's smaller than 0, then that's what. If it's the last one, the tank can be 0. So if it's smaller than 0, then it's no go. And then we do this, and then we will return this. Try this. Still not right. We're gonna refill it once. Right, so tank is 60, 50, 40, and then 10, right? Tank currently is 10. The position we want to reach is 100. The current position is this. And then tank become -30, right? Tank become -30. And then current position this. Go back up. Oh, we already hit the last one. The heck? So when we get out, we'll just do this one more time. If tank is larger or equal to 0, else -1. There we go. So when inside we do all this, and then outside we do it again. Okay, let's try these two. What the heck? Now these two don't work. Huh? What? I have a feeling I might just remove this. Okay, pass one, so we have to figure out this one. Okay, so first tank is 1. Right, tank is 1. Current position is 0. The position we want to reach is 10. Right? And then no, tank is not smaller than 0. So the position is 10. So tank equals -9. Right? Tank is -9. Oh, I shall not. When do we push? I'm putting the fuel in before I can actually use it. This is trying to go to the current position, right? Hold on. Let's. I'm trying to go to the current position, which costs my current tank to be looking like this. Then, if it's smaller, then I need to go up, go up, go up. And then we do this. Okay, this makes more sense. So we have to do this first to guarantee that after going through this, we can reach the current position. We can reach the current station. I say if this, and we return. Otherwise, we do this. Okay, so let's try these 3. Now they pass. Okay, I have a couple more. Now they all pass. All right. Oh, it still takes some effort to code it up. And this, I believe, is still important. Like if I comment out this, it's still working. So we don't need this because we do the tank thing beforehand. So we're guaranteed to have the correct value for tank. Don't do anything.
I can do it.
No. So we guaranteed that, I know it. When you hit this line, we know, right, what the amount of fuel needs in the tank. All right, and then we can just do this. So we don't need this line. Exactly, we don't need this line. And final thing, we tank, okay, all of this equal to index. Do we even need index? We haven't even used index. Current position, right? So like this, boom. All right, let's go. We can say this is O and login. Yeah, it's a tough problem because even after we understand the solution, it still takes an effort to figure out the algorithm. Oh, ooh, yeah. The amount of performance boost, ridiculous. All right, so we've done this. I'll see you guys tomorrow. Adios.